try this again. So we're going to start with lecture 3. We're going to talk about Intel x86. I already posted homework 1, so please review the homework and work on it. The due date is coming Tuesday. We talked about, in last class, data types, storage media, data alignment, and endiness. And today we're going to just first review a little bit operands. The data being operated on, that's what we talk about, operands. And how are the bits interpreted? And it could be integer, floating point, signed or unsigned numbers, and they could be byte, word, double word, etc. We have many different kinds of data storage. In this class, we focus on two major memory components, registers and memory. They are different in terms of capacity and speed. Registers are small, but they're very fast because they are on chip. And the way we use these registers is to refer them by names. Memory, on the other hand, has larger capacity but much slower than the register to access. And it's organized as hierarchy, although we didn't talk a lot more about the hierarchy of memory. In fact, when we talk about memory, we have cache memory, we have offstream memory, and for cache we have different layers of caches, but we're going to talk about those at the end of the later part of this course. The way we access data in memory is by using the address. Each location in the memory is a byte. The minimal unit we can access memory is a byte, and each byte has an address. When we talk about memory, and especially when we talk about multi-byte addresses, multi-byte data, you have to consider whether that data, either word or double word, is aligned or misaligned, because that will affect the load and store of the data, affect the performance. Endiness is how we organize the byte sequence of a word or double word. You can essentially have two ways to organize them. And in x86, we store the most significant byte in higher address, and this is what we call little endian. Addressing modes. Addressing modes refers to the ways of specifying operand location. Basically, we want to tell the microprocessor that where are the operands stored. And we have three location types. First is a register, or we can call it register addressing. We provide the name of register, and the microprocessor will read value, the operand from the register. The second location type is the memory. It provides address to the microprocessor, and the microprocessor will use the address to load the corresponding data from memory. There are several modes for specifying memory addresses. That is to say, to supply the microprocessor a memory address, we have different ways to do that. The third location type is basically in the instruction. So there are cases where you have these operands, especially the immediate values, are encoded into the instruction itself. Instructions accessing memory generates what we call effective address. Effective address is calculated as part of an instruction. So when the microprocessor tries to execute this instruction, the first thing it has to do is to decode the instruction. It has to figure out what are the components within this instruction, what are the information encoded into this instruction. The effective address can be used as actual memory address in a simple memory system, or it can be used within a particular segment in a segmented memory architecture. which we will talk about, and because that's one unique characteristic of x86 architecture. The effective address calculation can involve a constant value, for example, number 1, 15, or 256, and one or more values stored in registers. So you can think about that. You may have some part of the address stored in one of the registers, and then it's possible that you need to add that value to another value, maybe a constant number or immediate value. And there could be some combinations of registers and constants. Yes, we'll show you the examples. General memory addressing modes. There are memory direct addressing, which means we're going to use a constant value and use that directly as the address. The second, register indirect, is where we use the values stored in registers as the address. And the third one is so-called base plus displacement. So you have a combination of these first two. You not only have a constant, which we use as a displacement, but also you have some value that is stored in the base register. We can have variations of this mode based on number and types of registers. There are other types, for example, memory indirect and scale, and these are not commonly used. x86 refers to family of Intel processors. It starts with the first Intel microprocessor, 8086, which was released in 1978. And this instruction set, with some extensions, are still used in the current Intel processors. That's why we still call them x86. x86 microprocessors, or Intel's processor families, are general purpose processors. Depends on the actual processor, it may support 8-bit, 16-bit, 32-bit, or 64-bit data. That's essentially how big the registers are in the microprocessor. Some microprocessors, all their registers are 8-bit. For example, the PIC 16 families that we're going to talk about, those are 8-bit registers. For the Intel 386, and it has 32-bit registers. That's how we call it. It's a 32-bit processor because internally the registers are 32-bit. And x86 processor families allows both registers and memory operands. That is to say, as we saw some examples on Tuesday, there are instructions that use registers for their operands. For example, we have a ADD EAX, EBX, if you recall that instruction, and that instruction has both of its operands in registers. Some other instructions may have one operand in register, one operand in memory, and we also had example. If you remember, we have a data transfer instruction, move, and the first operand is a register. I think it's EAX, and comma, and then we have a bracket with a number in it. And the second operand, because we see a pair of brackets, that is to say that operand is a memory operand. And what does that mean? That means the second operand, the microprocessor is supposed to get the second operand from the memory. That's what we mean it's a memory operand. Because the bottom line is, in order for the microprocessor to execute that instruction, it has to know where the data are located. And then it can retrieve the data either from register or from memory and then perform the operation. x86 microprocessor use segmented memory architecture, which we will talk about later in this class. It has real and protective mode. Real and protective mode, this is two operation mode that the microprocessor could be operating in. At the very beginning, when you power on the microprocessor, the x86 microprocessor, it runs in real mode. In real mode, you have limited memory address space. You cannot do multiple programs, and there's some limitations in terms of the program space, the capability to access memory and I/O. Very quickly, when the microprocessor finishes the necessary operations in real mode, for example, it has to load the OS kernels from the disk, it has to prepare the peripheral devices. After that, it will switch its operation to so-called protective mode. And things are getting very fancy, very complicated when it gets into protective mode. And the reason we name it protective mode is because in protective mode, the microprocessor can actually work on or execute different programs. If you run your Windows operating system, which is based on protective mode, you can easily fire up different applications. You can open a Word, open an Internet Explorer, and you can run many programs at the same time. And these programs, they run smoothly and they would not interfere with each other. That is because the processor is running in so-called protective mode. Every program has its own program data space, and the operating system will be able to manage these sharings. So they have to share the same physical memory, and they have to take turn to run their instructions through the microprocessor. And that's all enabled by this protective mode. Okay, register set. Simply that refers to the set of registers available to the programmer for them to write assembly language programs. In Intel 386 microprocessor, we have 9 32-bit registers. We start from the so-called general purpose registers or data registers. We have EAX, EBX, ECX, EDX. Okay? And as you see in the top right, the first 4 rows are the 4 data registers. And again, the way we refer to these registers is by using their names. So if you want to do something, let's say you want to add numbers which are stored in these registers, you just put their names in the instructions, like add EX, comma, EBX. Out of this data register, EAX, because it's a 32-bit register, essentially it has 4 bytes in it. And this is the least significant byte side, and this is the most significant byte side. What we see here, the least significant byte, if you can see here, this is so-called AL. Okay, this little shaded box here on the far right, this is the AL. And next to it, this is AH. Both AL and AH are 8-bit registers. Okay, and and AH and AL together, these two, is called AX. So if I tell you, this is my EAX register, you see it? And I have 4 bytes here. Let me just give them a number in hexadecimal. if I tell you EAX has these 4 bytes, then what is the value in AL, AH, and AX? This is 56, and this is 56, 7, 8. Okay, if I really want to confuse you, I want to ask, is that right? Which one? Gotcha. Okay, since I confused you, there's no swapping anymore here when we talk about registers. This is AL, this is AH, and this all together, this is AX. Okay. So whatever value is there, that's the value. And we can do the same thing for EBX, ECX, and EDX. Those 4 data registers, they can be used in the same way. And in this particular diagram, we have this RAX, and this is for the 64-bit 64-bit machines. We don't have to pay much attention there. We have 2 pointer registers, EBP and ESP. Those are used to refer to certain locations in segments, for example, the stack segment. And we have 2 index registers, ESI and EDI. And we have instruction pointer, EIP. We have 6 16-bit registers, and these are called segment registers. This CS refers to code segment, data segment, stack segment, and then actual segment and FS and DS. In this class, we'll do a lot of things on PS, DS, SS, sometimes ES, because the code segment is where the program instructions are stored. That's why we call it code. Programs are stored in the code segment, and the particular location in the code segment is given by this IP or EIP. We'll look at segmentation management. Last thing I want to mention here is the flags register. In some machines, some processors is called status register. This E flags, well, A flags is here, wait a bit. On the 64-bit machine, we have some extensions. This is the register that each individual bit means something. If that bit is 1, for example, if CF, carry flag, out of the flag register is 1, that means the computation the processor just performed generated a carry flag. Okay. This flag register is just the aggregation of these flag bits to indicate what is the outcome from the previous computation. Now you may wonder, why do we need to remember this status or results? It's not the numerical results. For example, if you do addition, the sum of these 2 numbers will go into the destination operand. But this flag we're talking about is the carry flag, sign flag, this kind of non-numerical values of that previous computation. We do need these status information for very important operation. For example, if you want to do a for loop, okay, you want to do I plus 1, and you want to check whether I exceeds the threshold. The condition checking is going to rely on these status bits, because using these status bits, you will know whether I is greater than 10 or not. So the next instruction can make the proper decision. So that's the reason we have this flags register. With 64-bit machines, starting from Pentium 4, we have these extended registers. All the data pointer, index, IP flags are extended to 64 bits. And we have 8 additional data registers. Okay, we come back to the general purpose data register, and I explained to you that we have 4 general purpose data registers, A, B, C, D. We give them names: accumulator, base, or count data. These names don't really matter that much. What we do want to know is these data registers can hold 8-bit, 16-bit, or 32-bit data. And the way we refer to the lower bytes or lower word is by using AH, AL, AX. So given the value in EAX, you should be able to figure out the value in AX and AL and AH. The common usage of these registers is to hold data such as source or destination operands for most operations, including, for example, addition and shift operations. We can also use these registers to hold pointers for accessing memory. We'll see more examples later. Some of them have dedicated use. For example, C is including ECX, CX, EAL, CH. Those are often used as counters for loops. So if you, let's say you count a for loop and the number of iterations is 10, then in C you will say for I equals to 0, I less than 10, and I plus plus, and you can do the loop iteration. In assembly, once that C program is converted to assembly, you will see that this counter, this I is corresponding to the counter register, to be a CX, a CL, CH, and the assembly language program will use that as the loop counter. So B is BBX, BL. These are often used for table lookup translations, space addresses, and for D, we use them in the I/O instructions. Pointer registers. Stack pointer register, ESP and SP. Those are for accessing information within a stack. So I keep mentioning stack or code segment, stack segment. These are the one of the 6 segments that the microprocessor maintains. And just let me just finish this explaining these registers, and then we're going to go into to see, okay, what is a stack and how do we find information within a stack. The other pointer register is the EBP and BP, and that's called base register. This BP or SP, these are offsets. So let me have a very simple illustration of a stack here. So this is the memory, okay? Depending on the mode, real mode or attacking mode, you have different size, but this is a big whole memory space. And out of this memory space, we could have code segment, and we could have a stack segment. could have data segment too. And each of these segments is 64K bytes. And it starts with some address and end with some address. Using this code segment as an example, so in order to find the actual instruction need microprocessor to execute, you will need an offset. Okay. You will need to give an address, example 1, 2, 3, 4. Okay. And this 1, 2, 3, 4 will tell you that starting from the beginning of the stack, you need to go this far to find that word or double word. That's the offset we're talking about. Similarly, for the stack segment, we start from 0, and then this SP is a 16-bit register. It has a value. So it could have 1, 2, 3, 4, it could have something else. But this value will tell me how far I should go from 0 to get to that piece of data. And this SP and BP, they are specific for the stack segment. You don't use SP or BP for the code segment or other segments. So that's kind of one special thing for the SP, BP to pointer registers. They are specific for the stack segment. And we'll later talk about more about stack. But right now you should know that this SP, this SS colon SP, this points to the top of stack. And we'll explain later how special that data is on top of stack. Two index registers, SI and DI. SI is the source index, DI is the destination index. Both of them are 16-bit registers, and then with extension, ESI is a 32-bit, EDI is also a 32-bit register. The way we use them is very similar to these SP or some other offsets. So they are used together with a base register to find particular data within a segment. We often use SI and DI together with this data segment register, DS. So you can imagine that you will have something like here, you have a data segment. So this is the data segment. By the way, the way we draw it, I don't mean that this data segment is going to be overlapping with the code segment. You can imagine that this DS could start anywhere in this region. So you can have a separate code segment, then data segment somewhere else. And they're not supposed to be overlapping with each other. So you can have ES, SI. So it depends on the actual value in SI, you will get to that particular data in this data type. Okay, we now going to look at this flags register. In Intel 386, well, before Pentium, we have a 32-bit register holding the single-bit status and control information. As we see in this example, in this diagram, we listed the all these status and control bits, and we explain them, some of them. And also we show you that what are the bits available for different Intel processors. You can see that as the Intel goes to newer processors, it tries to use more bits from this register because there are more information to remember. There are two categories. So out of all of these bits, there are two categories of information. First one is the status flag. Status flag or status flags are used to report the conditions resulting from instruction, and most often this instruction just completed. Most of the instructions update status. For example, when you have two consecutive addition instructions, when the microprocessor executes the first one, after it's done, it will update some of the flags. For example, the carry flag. Sometimes there will be a carry bit generated, so the carry flag will be updated as a 1. Now, right after the first instruction, the flag bit is updated, and the microprocessor will continue on the next instruction, which is, for example, another addition instruction. And the second addition instruction may or may not generate a carry flag. Let's say it does not generate a carry flag. Then after the second instruction is completed, the carry flag bit will be cleared, will be set to 0 to indicate that, oh, for this instruction it just finished, no carry bit was generated. So these will be these status bits will be updated very frequently, basically instruction after instruction. But of course, that depends on the actual instruction. Some of the instructions may not do updates on the carry flag. For example, if it's the data transfer instruction, when you move AX, BX, move instruction does not generate any flags. So that will not affect the carry flag value. And once we have these status flags, and we can do a lot of condition checking. So there are conditional branch instructions or conditional jump instructions. So depending on the actual value on the flag bits, the jump instruction may or may not jump to the target address. We call it taken or not taken. The second category of the flag bits is what we call control flags. Control flags are supposed to be written by the programmer to control the processor function. It is used by software to turn on or off the operating capabilities. For example, there's interrupt bits and real mode, protecting mode bits, which are supposed to be updated or written by the software to kind of change the operating status of the processor. Okay, so now we're gonna look at the big thing in the memory of x86, the segment. x86, it has a so-called memory space, which is shown on the right side. We have, starting from the bottom, we have regions that's primarily used for systems. For example, used for the interrupt vectors, used for basic I/O instructions. And beyond that, you will see some system area, and then go further, you will see so-called extended memory, which is used for general purpose computing. So you can load program data onto these extended memories region. Think about when you run, let's say, a Windows operating system, you will have, it takes probably 1 minute for the OS to load it up, or half a minute, depends on the machine and depends on the OS version. This lower address space are used to store important information related to operating system. And once the OS is up, and you can run your favorite programs, Internet Explorer, Microsoft Word, and those programs, those applications will take the higher part of the memory region. Memory address space. We're going to use this term a lot. Memory address space. This refers to the size of the whole memory region. 1 megabyte of real memory, that's the system plus transit program area, and then we have extended memory size, and that depends on the actual processor. We have input and output address space, or I/O address space in short, and that is 64 kilobytes. This I/O address space could be overlapping to this memory or could be isolated, and depending on which one, we're going to see different way to access the I/O devices, but we'll talk about that later. Okay, let's say we're running the Intel 36 microprocessor in real mode, and that means it can access 20-bit memory address. Okay. Oh, you don't see a 20 zero because those are hexadecimal zeros. So we have 5 zeros here and 5 Fs on top, and that's 20 bits. And you can calculate that this 20 bits actually gives you 1 megabyte of space. Okay. And it's good to know that you have 1 megabyte of space, but it's kind of sad to know that the microprocessors, the Intel microprocessors, do not use this 1 meg at the same time. Let me tell you why. The way the microprocessor uses this memory space is by relying on these segment registers, or the segments. We mentioned code segment, data segment, stack segments, and we have total 6 segments. And these segments are the active sections of memory. Okay. Note the word the active. And that means at a time, the microprocessor can only access these 6 segments. And each segment is 64-bit. So you're talking about 384 kilobytes. Okay. And to give you some numbers. Each segment is 64 kilobytes, and with 6 of them, so that's 64 times 6. That's 384 kilobytes. And how big in total we have? 1 meg. Okay, that's probably 1/3 of the whole space that the microprocessor use at any given time. Now, that doesn't mean that the microprocessor can only access these 6 or these particular regions. It can switch the region or change the location of these regions to other part of the 1 megabyte of space. So as a result, the microprocessor can eventually use all of them. But at any given time, only the 6 regions, 6 segments are active. Segment size can be fixed or variable, depends on the mode. And in the first half of this class, we're going to talk about the real mode. So you can assume that the segment size is fixed. And each is 64 kilobytes. Architecture requires registers to store start of active segments. In my diagram here, we have the stack segment SS:000, that's the starting address of my stack segment. And in fact, we use this SS to store the start of the active segment. because this 0, you can kind of assume that everybody can start from 0. So what we really need is this segment base register, this SS or DS or CS. This register, well, one of the 6 registers is, all these 6 registers are used to store the start of the active segments. Each real mode segment has 64 kilobytes, and we have 6 of these programmer controlled segment registers indicating the start of each segment. And one of the 6, they are here. CS, that stands for code segment. SS stands for stack segment, and DS stands for data segment. Then ES stands for extra segment, and then you have FSGS. I don't really know what they stand for. As you see on this diagram, by using the values of these 6 registers, segment registers, we are able to find the location of the corresponding segments. To be more specific, we are able to find the starting address. For example, here GS, the starting address is GS colon 000, so that's here. And as you can see, by changing the values in these registers, you can essentially move these segments up and down. Each segment must start on 16-byte boundary. And here's a list of example starting addresses. You can start from 0000 or 00010 and 00020, etc. So those are hexadecimal values, and all of them, their least significant hexadecimal digit is a 0. This is 0 here, 0 here, 0 here. Those are the valid starting addresses. Later, when we look at the address translation, we will understand this means the same thing. We have 0 as the offset as the starting address. The total active memory is 384 kilobytes. And how do we get that number? 64 times 6. We have 64K code segment, 64K stack segment, and we have overall 256 gigabytes over 4 data segments. Okay, we have 2 pieces to address in segment memory: the starting address of segment and offset within segment. And we are showing example here. To locate any information within the memory or within a segment, what you need is 2 pieces of information. First, the segment, and then the offset. If you see all the address I wrote down on this diagram on the board, every address has this segment with address. And some of them, like here, the offset is given as constant numbers. Some of them, those are register, okay, pointer register. But everyone has 2 pieces, segment and then offset. Okay, if you look at this again, ES, we know this is a 16-bit register, right? And all of these 7-bit registers, these are all 16-bit. And this one, this value here, this is a 16-bit, right? 4 hexadecimal digits. Same here, this SI, this again, is 16-bit. Right, everybody's 16-bit here. Now we're talking about something strange. Looks like all addresses are 20-bit address in real mode. Let's do this 2 to the power 20. That gives you 1 meg. That's why we say at the beginning, in real mode, the processor has all this 1 megabyte of memory address space. That's total overall. That is to say, if we start from here 0, okay, and the last address in this memory space, this will be 2 to the power 20 minus 1, because we're counting from 0. If we look at this, we call this physical address. And because we have 20-bit, so we are able to access 1 megabyte of memory address space. And to access these data, the microprocessor will have to provide a 20-bit address to the actual memory chip in order to access any individual byte. Okay, that's the story about the 20-bit, the network memory. So there's something seems disconnected. We have two 16-bit, and we have on this side we want a 20-bit physical address. And it has to be some kind of translation. Has to be some kind of translation. And indeed, there is a translation. Segment registers hold upper 16-bit of segment base address. Where are the lower 4 bits of the base? We're going to use the second piece here as the 16-bit offset. So why is the offset 16-bit? Because the way we use these registers, this side is 16-bit, and these are 16-bit. But the fundamental reason is every segment is 64 bytes. So let me remember 2 to the power of 16. That's 64. Okay. So each segment here, this is 64 bytes, and this is 64 bytes. And that's why I only need 16-bit to kind of address anywhere within this segment. But don't need more. Each one is 64 bytes, and 16-bit will be enough. Okay, I still haven't told you the translation. Okay. All right, here this lower 4 bits always 0 because it's starting from at multiple of 16, and here we have the 64 bytes of segment size. Those are the reasons. Let's see here. Okay. So we're gonna still keep that problem and the question unanswered. How do you go from two 16-bit values to a 20-bit value? We'll eventually get to that. Here, within the instruction, address is combination of segment register and effective address. In general, we use this kind of form, SBA and EA, and everything here you saw. SBA, EA, SBA, everything here is the same. That's how, in general, we're gonna refer to a memory location use that kind of address, SBA and EA, so segment-based address and effective address. And EA based on addressing mode. We'll later talk more. And these are some examples. CSIP, This is segment base address, and this is the effective address, or the value in IP. And then segment base address, and this is the effective address. Of course, the value in SP is the effective address. And here's an example. Data segment column 0100, and this is segment base address. Of course, the value in it is the segment base address, and then you have this constant number as the effective address. Okay. So we're going to use this information to find the linear address, and that is the program generated location in the memory space. So in real mode, the linear address is the same as the physical address. That's 20 bit. That's what we need to use to find the actual data in memory chip. Okay, here's how we're gonna do the translation from the two 16-bit values to the 20-bit value. We have an example here. This address, the segment base address is 1234, and the offset is 0022. Both are in hexadecimal. We can write the equivalent binary representation of this value, and for the SBA and also for the EA. Okay, and we'll do one thing. Actually, we have two steps. First step is to do shifting the base address to the left for 4 binary bits. Okay, because both 4 zeros are the new zeros added to the end because of the shifting. Okay, you shift the 16-bit to the left for 4 binary bits. So those are new zeros at the end. So that gives you the hexadecimal value 12340. And this 0, you know, that's 1 added because of the shifting. So that's the first step. The second step is to add the binary segment address and the offset. So what you can do is you can add this value to the binary offset. Okay? So you have this value here, and this is the offset in binary. So you have this sum, and that is 1, 2, 3, 6, 2. If you convert it back to hexadecimal. You can do all these shifting and addition in hex without bothering converting them to binary, because you're simply doing the same number, although the representation is different. So in hex, what we do is we're going to shift the hex value, the original hex value 1234, to the left for 1 hexadecimal digit. That's equivalent to 4 binary bits. So we do shift, okay, and that's why we have a 0 at the end. So shift to the left 4 bits, that is adding a hexadecimal 0. And then we're going to add that to the offset, again in hexadecimal. And the hexadecimal 022, so the final result is 12362, the same as we did in the binary. If you check the final result, this is actually a 20-bit value. Okay. The magic was because this shifting. We did shift, and we do the addition, and we got a 20-bit value. And that's the linear address for the actual memory location. In program, when you write a assembly language program, what you really care, or what you're going to use, is this SBA, segment base register, and the effective address. This translation is done by the processor itself. You don't really do that in your program. You don't. But here, I just want to explain to you what really happened inside the processor before you can access the actual value in memory. Okay. Okay, I think just a few more slides after the break. Boundaries of the segments. We have 6 active segments, and each segment is 64K bytes. Total, we have 384K bytes of active memory. And we start from 0, we end at FFF. And 0 is lowest address of the byte, and FFFF is the highest address of the bytes. The address of an element of data in the data segment, here's an example, ES colon BX. With this, okay, you know you have a 16-bit here, 16-bit here. With the shifting and the addition, the microprocessor will be able to get 20-bit address. That address can be used to access a byte, a word, or double word. And if you recall, we can use the address to access byte, word, or double word, but for multi-byte words or double words, you are talking about some alignment issue, right? And with that address, you know whether it's a aligned double word or misaligned double word or aligned or misaligned word. So this example, if you look at this diagram here, what we show you is the microprocessor and together with the memory. So again, we're talking about 2 different components. Microprocessor here, memory here. Don't mix them. DS and BX, both of them are inside the microprocessor. They are registers. And from these 2, we will be able to find the location of the data segment, because the DS will tell you that. And DS colon 0000, that's the beginning or lowest address of the data segment, and up to the highest FFFF. This BX will be used as offset. So what you will find is, using DS colon BX, you will find the location. One thing I don't really like this diagram is that it's kind of confusing here. This DS colon 0000, this is the address. So this really should be labeled outside the box, because the value here is the actual data. Okay? Similarly, this DS colon BX really should be labeled outside the box, because inside the box, that's the actual data. So just be aware of this diagram. Okay, we'll end this part of the lecture here. Next time we'll talk more about x86 memory, and we're going to talk about assembly language programming basics. Okay, let's heading to the break. Just 1 sec here.